All right, so we're ready for the second talk, and we also kind of switch gears now. So this is kind of a general idea, like, I mean, the organization of this workshop, like to kind of mix different subjects together so that, like, everybody can, like, hear a little bit of other subjects that they're not necessarily working on. So we're very happy now to have Stavros Mougiakakos, who is going to tell us about QFT-based methods for classical gravity. So please.
So good morning, everybody. So before starting, I would like to take my turn in thanking the organizers for putting together this nice workshop and also for the invitation to speak. So, okay, as the title suggests, I will speak about some methods which are inspired by QFT, quantum field theory, and they are used for classical gravity. So it's like a relatively recent subfield that has emerged in the field of scattering amplitudes and effective field theories. So, okay, I will try to split the talk into three parts. So the first is like a motivation of how and why we use the stuff. Secondly, I will try to give some rough sketch of how these work. And finally, I will refer to these two recent works that are trying to extend these into a new expansion that I will talk about. So, okay, let's go. So I suppose most of you are familiar with the story of the detection of gravitational waves. So this happened roughly 10 years ago. In practice, we entered this so-called gravitational wave era after the observation, due to the fact that now we have the chance to do multi-messenger astronomy, to have an observational window on strong gravity, to search for exotic objects, new physics, and anyway, whatever one wants to do with these observations. The important point is that all this story relies heavily on how you theoretically predict your signals, because the signal is very weak. It has a lot of noise. So all the detection lies on the theoretical template, the gravitational waveforms that we call, in order to identify and extract the physics out of that. So in practice, this story brings us to the accurate prediction and the two-body problem in gravity eventually. So what we want to do is to solve the two-body problem in gravity, construct the waveforms, and use them to do this masked filtering in order to identify the signal. So let's see what is the typical event. This is a typical event that we are observing. So they are comprised by these three phases, the in-spiral, the merger, and the ring down. So what I'm going to talk about mainly is the in-spiral, which can be subject to an analytic treatment, because there you can use perturbation theory. The merger is solely treated in numerical relativity. It's a very violent event. And in the ring down, also numerical relativity and black hole perturbation theory can be used. But okay, let's focus on the in-spiral phase, because analytic treatment is what I want to talk about. So let's see. Here I'm trying to sketch the general pipeline that one uses when they want to construct these waveform templates. So besides numerical relativity, that is a very core method that is being used, other methods which are purely analytical can be used in order to extract dynamics from there, inform this effective one-body formalism, the so-called effective one-body formalism, to construct the templates. So in practice, we will forget about the left bottom side of the slide, and we will focus on these three perturbative expansions that are being used. So these are the main three. So let's take them one by one. The post-Newtonian is, let's say, the most straightforward. One expands in the coupling coefficient of gravity and the V over C. This is a double expansion, but of course for bound systems they are connected through the virial theorem. The point is that you have this double expansion. Now in the post-Minkowskian, one treats the problem relativistically. So you have only, it's a weak field expansion, so you have only expansion in G, but not in V over C. And in the cell force expansion, here we adopt a different point of view. So it's not a weak field expansion. It's an expansion over the mass ratio. And in principle, it's used for extreme mass ratio in spirals. So, okay, let's see the connections between all these expansions. Let's focus on the post-Minkowskian and the post-Newtonian. So, as I told you, one can see the relation between these two expansions in this way. We see that if you take and expand the 1 PM order, the so-called 1, this is a resummation of the velocity contribution. So in a sense, if you have the 1 PM, you have infinite amount of terms of information that contribute to relative Pn orders increasing and to infinite order. So we have to understand it in this way. The PM resums, in a sense, the Pn. Of course, this is a rough sketch. It's not that it works exactly like that, but just to have a power counting idea. So this is the way these things are connected. But there's also a similar connection between the cell force and the post-Minkowskian, which goes like that. So the zero cell force is let's say, the geodesic motion. And indeed, one can understand in a similar way as before that if you expand the geodesic motion, you recover again infinite amount of terms in the post-Minkowskian expansion. And indeed, here the scaling is even better because you can get up to 2 pm completely from geodesic motion and also for free the rest of the terms. So if you symmetrize again between the two bodies, you get the complete answer. So what I want you to keep from here, from the previous slide, it's that all these perturbative expansions have a relative connection between them, and you can transfer information from one to the other. So it's like a synergetic way to work and inform and cross-check also. So let's see the methods that one can use. So in practice, I decide to group in two parts. One is the GR perturbation. So let's refer to them as more traditional methods mainly because they pre-existed, to be fair. So here there has been a lot of work in all of these types of expansions. But more recently, there's this effective field theory and scattering amplitudes approach that, let's dub it, modern methods, in contrary, which has tried to, with these techniques, we have tried to address these expansions. In practice, up to today, we have been addressing the post-Newtonian and the post-Minkowskian, and they come in chronological order. So, let's say in 2004 around, the post-Newtonian expansion was treated using these kind of methods, and around 2015, so 10 years later, also we started applying in the post-Minkowskian, and now 10 years from then have passed. So in practice, it's time to consider how one can use the cell force if we want to be consistent with the calendar. So I will try to roughly sketch what are these, how these things work. So bear with me a bit if you're not familiar. So here I will focus on worldline approaches. So there's a sub-distinction in these modern methods that one can use worldline methods or purely QFT methods. I will not bother with all this because it's a complication. Just keep in mind that there's also another way to do this stuff, but I will focus on one branch. So the typical event looks something like that. And we know that there's an hierarchy of scales. So we have 3 scales in the problem. So we have the Schwarzschild radius, the orbital separation, and the gravitational wavelength. And these are highly separated in the spiral phase. So in practice, this kind of a setup screams for an EFT description because we can split the regions of the problem in 3 independent ones. And by matching each region, we can recover the whole solution, but we can treat them independently up to some point. So this is what we do. This is the idea. In practice, we focus on each scale at once, and we solve independently, and then match. Now, if we want to split it into some points, so the Schwarzschild radius scale of the problem is, let's say, the most resolved and trivial in a sense, because we take the point-particle approximation. So we assume that we are far away, which we are, and we see the black holes effectively as point particles. And using the symmetries of general relativity, we can write down an effective action for this point particle, where here we have the minimal coupling for a point particle with spin, and then you can compensate with higher derivative interactions and non-minimal couplings to describe your finite size effects, and so on and so forth, absorption and whatever one wants to describe. Secondly, we are treating also general relativity, the bulk theory, let's say, where we embed the 2-point particles as an effective field theory as well, where the first leading order is Einstein-Hilbert, and then of course one could compensate with higher derivative interactions. Here the point, in practice we are using general relativity to be fair, and the rest we kind of not deal with them yet, but the point is that this is a generic and adaptable setup to consider also modifications of GR. Finally, since we are working with amplitudes, we are used to working with amplitudes in flat space. In practice, we are doing weak field approximation. So we expand the metric around Minkowski, and we quantize effectively the perturbations, the gravitons. After doing this setup, we want to extract this effective theory. So we write down our Feynman rules, and we compute loop diagrams. So I will show you in a bit why we need these loops. The point is that the whole computation comes down to constructing multi-loop Feynman integrals and solving them. Finally, since the problem can be, it's kind of adjusted, so you have to specify your kinematical region. In the PM expansion, for example, in practice you are dealing with a scattering problem, so there's an extra point that the scattering problem is not something that we are observing as an event. So we need to translate this information to the bound problem, and this is what is being done with mapping between these kinematic regions of bound and scattering systems. I will not talk about that, but have in mind that we also have such tools. In very practical sense, we have on the left-hand side our effective action, and here on the right-hand side we have Einstein-Hilbert, okay, the gauge fixing as always, and the point particle. And we are integrating out the graviton. This is how we extract the effective theory of these point particles interacting. In the language of worldline approaches, integrating out gravitons is equivalent to focusing on the classical physics is equivalent to not taking into account closed graviton loops. So here it's just a rough sketch again up to g cubed of the diagrams that appear, because this is how in practice we are integrating out the gravitons. So this is the tree level, this is one loop in a sense, one loop because it gives a one loop Feynman integral, and then these are two loop stuff that give g cubed, so it's like an L plus 1 the counting. So how much time do I have? I have a lot. Nice. Okay. So I spoke before about the cell force, which is a third, let's say, expansion, and that it's kind of time to start thinking how to apply these methods in the cell force. So at least in my opinion, in order to do that, it's necessary first to have a self-consistent framework for the Schwarzschild. I mean, this is the simplest thing one can do, one can think of. And we want to address this, the Schwarzschild metric, and recovering it from these techniques, just to make sure that we do everything correctly. So it's a strong cross-check, at least that we don't do wrong stuff. But in general, the idea of SF-EFT has also been initiated by these groups. And it's something that I think that in the future it's a promising avenue. So let's go and focus on what we did in these two works concerning the Schwarzschild metric. So here we're going to go into the more practical sense, so I hope you will get a better idea. So we have on the one, let's think of it in this way. We have on the one side the GREFT description of general relativity, and on the other hand the truth, the real theory, the general relativity. And we want to match the two solutions. We know from GR what is going on, so it's fine. So we want to compute it from here. And the equivalence of these two descriptions, of course, is up to the choice of degrees of freedom that we are comparing, we are matching, and the choice of the gauge. So we're going to use the harmonic gauge because it's convenient for us, and we're going to make this expansion, as I told you before, for the metric tensor. The expectation, which was already there from 1974, so it's a pretty old idea in a sense, is that if you go and compute the the graviton emission, the off-cell graviton emission from, okay, here it's a scalar field, but also one can work in world lines and just have a local source. And here this blob represents the loop structure that you can include. The more loops you go, the higher g to the n plus 1 terms you will get in the metric. So in a sense, you know the result, and you want to make sure that you get it from your techniques. And it's a matter of loop orders that you compute. So the expectation is this. Go start adding loops, and you get the terms of the metric order by order in G. The problem is that it's not that trivial in the end of the day. Actually, it was much more complicated than expected. And indeed, in this work here, like 4 years ago, we tried to do this, at least to investigate how this computation indeed scales. And there are two main problems when dealing with this off-cell quantity. So the first is that you have intermediate UV divergences that come from your description of the point particle. And they are intermediate in the sense that we know that they are a gauge feature, but indeed, in order to be self-consistent in between the computation, you need to take them into account. And this is an infinite hour of these non-minimal couplings that you need to add to regularize your stress tensor and your subsequent metric. The second is that there is no algorithm for higher loops, so we went up to 3 loops, but going higher it's a bit of a pain. And this is connected with a known fact that when you go and treat GR in this way and you expand, the Feynman rules that you get for the self-interactions of the gravitons are super annoying and very complicated. But the most important point is that they go up to infinite order of self-interaction. So you can have as many gravitons self-interacting out of there. And this is, in practice, what is obscuring you from creating an algorithm to go from one loop to the other. Because we said that we want to do something to all orders in G. So if you want to generalize, you need a recursive way to build your loop expansion. So we took a step back. It took some time intermediately. But in the end, we managed to succeed in this idea. So let's see. We take this for granted this way. And indeed, in these amplitude descriptions, this is the way that people do stuff. But if you remember before, in the EFT, in practice, you are integrating out these degrees of freedom. So in practice, why should you care how you parameterize your graviton? You shouldn't care. You should pick the most efficient way to do this. And indeed, this is what we figured out in the end of the day. So inspired by this paper by Chung and Remen, which for here this is not the title, but the cubic formulation of GREFT is the point of the paper, the part of the paper that we are using. So what happens here? One can write down the Einstein-Hilbert action with respect to two degrees of freedom. So one, the Gothic metric. So GR people have been using the Gothic metric as a description. It's just that in amplitudes we didn't want to do that because it seemed more complicated. Finally, it seems that it's even less complicated. And the lesson to take here is we should pay more attention to what other people do sometimes. So we use as a degree of freedom the Gothic metric, the inverse Gothic metric. And then we are also introducing this extra auxiliary field which is connected to the connection. It seems unorthodox, but it's necessary in order to rewrite exactly the Einstein-Hilbert action with respect to only cubic interactions. And in a moment we will see why the cubic interactions is important. So having this, this formulation looks a bit like the Palatini formalism for those who work on that. But for us, the point is that we want to constrain to the 3-point. Again, we have to make a choice of gauge. Here, for the people that are a bit more familiar, they know that the harmonic gauge is not a unique choice of gauge. It's up to an integration constant. And this is, in technical terms, this is super important in the end of the computation. But probably I will avoid this discussion unless somebody asks. Anyway. So we take this formulation of GR and we couple it to the worldline as before. We write them with respect to our degrees of freedom, blah, blah, blah. The point is that we want to compute these currents to all orders in G. Indeed, we know that these depend on a single multi-loop master integral. It's a multi-loop bubble in the end of the day. And so there's a correspondence of the simplicity of the Schwarzschild solution to the simplicity of the amplitude side computation. Here we have a very simple solution on the Schwarzschild side, and on the other hand, we have a multi-loop bubble, which is pretty simple in Feynman integral language. So we can parameterize our currents, which are like the Fourier transforms of the fields here, with respect to 8 form factors. 7 of them are independent in reality, but we don't make this. We don't use this assumption, but we prove it explicitly out of the computation. So here, let's explain the notation. This n is the order of G that appears. So all these depend on this rho parameter, which is defined here, and in practice it's counting the powers of G, and it depends on the momenta, on the outgoing momenta of cell. So the game in practice after this parameterization is to figure out these form factors to any order in n, put them, replace them, resum them, and see if we've got the Schwarzschild metric to any order. A bit of the diagrammatics to make a sense of this story. So the Feynman rules here are the following. We have the the Gothic graviton coupled to the worldline. So here this is the trivial part. And we have managed to constrain, but just by introducing, and here I would like to take a minute to appreciate that. We have started from a theory that we have 1 degree of freedom and we have infinite amount of self-interactions. And we have rewritten in a way that we have 2 degrees of freedom with 3 interactions. So it's a super simple formulation. And this is the reason why we can generalize to all orders. So let's take an example of the g to the cubed, which is like a 2 loop. One can take the sum of these diagrams that needs to compute for the g cubed and can recognize a substructure here, which can be written with respect to the previous order. I suppose you understand where the story goes. Seeing that there is a substructure, we can write with respect to the previous order, and we can generalize this as an iterative structure to all orders in the loop expansion. So we are computing recursively each loop, and we are recycling this information. And indeed, this is the only way to get something to all orders. You need to find the way to build it recursively. Now let's see why this cannot be done with if you have the higher point interactions. If you had the 4-point, for example, here, you should add also the diagram that has here the 1 leg outgoing and 4 legs here, 3 legs here connecting to the worldlines. Now this would be a new topology, and it cannot be written with respect to the previous one. So at each order, you would have a new topology that enters that you cannot recognize as a structure from before. So this is the point why you need to have a finite. It's like combinatorics for the binary trees. It's not something super special. Okay, we have this iterative structure to all orders. It comes due to these 3-point interactions. And indeed, we can write down a recursion relation. This we compute it. It's not up to, it doesn't come from an assumption or anything. We can write down recursion relations for all these form factors. These are solvable at d equals 4 exactly, and there is no UV divergence. Now, furthermore, I mean, we have this closed form at any order n. So you just plug them back in as I promised. You resum them, and you get explicitly the Schwarzschild solution. Okay, I will see later if I will return to this point. Okay, I have time. I will say it now. So the GREFT computation picks some gauge. As I told you before, the harmonic gauge is non-unique. It depends on an integration constant that you have because it's defined by a differential equation, the condition. So if you put this integration constant to 0, then you land up to what you find in Wikipedia for the harmonic gauge. But in practice, if you don't set this to 0, you don't have a non-invertible form of the transformation. And the problem there is that if you don't have the invertible form, you cannot find even what you are looking for on the GREFT side. So it's subtle what integration constant your EFT computation picks. And in practice, the previous computation that I referred to, that we were having the UV divergence, etc., was internally picking another integration constant, and this is why we're getting these UV divergences. So in this formulation, in practice, you solve both problems at once. You have the recursive form, you avoid the UV divergences, you can use this stuff to go higher in the SF in principle, which at least for now we haven't done it. But what I want to discuss now is, okay, we got the metric, but we want to solve the complete problem of the geodesic motion, so we want to get the geodesic equation in the end of the day, which is not identical in our case, due to what, okay, I will explain why it's not identical. Let's see the setup first. So we want to build some cell-force effective field theory, or whatever name we will give it. So how this happens? Exactly as in the PM. I mean, it's not something new. Again, we want to extract an effective action from the original theory that contains here H is for heavy particle, capital M is the mass, and the light particle will come with a small mass here, you will see. So we write down the complete theory. We want to integrate now both the auxiliary field and the Gothic graviton to get the effective action. So we will do this again in diagrams. The only difference, and the reason why we will name it in another way, is that we will presuppose an expansion in powers of small over big M. So here we have the leading order, which is just in the rest frame of the big the big compact object. It doesn't necessarily need to be a black hole. The big compact object will just be there in the proper frame, and then we will have an effective action that we will need to compute from the diagrams by integrating out. that will scale with powers of m over m. The L0, for example, you see that it's going to be proportional to small m, and so on and so forth. Also, in order to set up this expansion, we need to self-force expand the trajectories as well that we were going to iterate later. Anyway, we just do this again in powers of m over m, and you see that the leading order term here, it's just the proper time. It depends on the proper time. For the light particle, the leading order equations of motion is the geodesic motion. In practice, I want to show that how we get the equations of motion for this from this effective L0 action. Now, what is the problem here? I lied a bit in the sense that before in the metric computation, I showed you only this interaction of the Gothic graviton, but this is not complete. Due to the expansion we do, we exchange the complexity and we have arbitrary amount of gravitons emitted directly from the worldline. We don't have, in the theory, a direct coupling of the worldline with the auxiliary field, but we have multi-graviton vertices. So in order to compute this L0, we need to compute this infinite amount of diagrams. That they are fun diagrams, they scale like that. Additionally, so we have one is that we have infinite diagrams. The second problem is that here the below couplings, the square couplings, here these are the big mass couplings, insertions, and on the top are the small body insertions. So you see even from here you understand that each of these contains a power of small m, so just this is the way that the power counting works. So at one SF, one would require to have two insertions of the small mass on top. Anyway, this is for generalizations. But here the square, in practice, is a sum over all the orders of the dressed graviton. So we have dressed propagators that we computed before. This is the metric. And all these emissions here are the dressed stuff. So we have a second infinity that we need to deal with, which is that we have put it here secretly because it's going to be a mess if we write everything. So how can we do this computation? I mean, in the end of the day, it's not very, I mean, I present it here, so we managed to do it, so it's not a spoiler, but I will try to explain a bit how we do this. So we want to split into two parts the computation, where we define a tensor here, tau capital, which is in practice it's trivial. It's like the contractions from the Feynman rules here. It doesn't contain any momentum dependence. And the important part is this calligraphic I, which is coming from actual loop integrations. So we don't care for that now. Let's say that we have a control over it. I mean, in the end of the day, you can't control it. It's just combinatorics. And see here what happens. So here one starts. Okay, I know the notation is a bit compact, but the point is that we have a Fourier transform over the exchange momentum k, and we have an infinite amount of loops that needs to be integrated, because the more legs here, the more loops you have. And this has to be integrated. The argument, the integrand, is this series over all of these n1 to nl, where L is the amount of the propagators here. So it's a bit messy. The trick here is to use, so we start from a Fourier plus infinite loops, and by using just the integral representation of the delta function, we see that this decouples all the loops. So you end up with an infinite amount of decoupled Fourier transforms. So this can be put under control. In a more simple language, the point here is that the interplay between the Fourier transforms and the loop integrations, the flexibility that we have in this language to play between them simplifies and trivializes a computation that, if you see it from before, I mean, it's impossible. You cannot even do it in the computer. You cannot put it in generality. So we get a closed form for that. In the end of the day, one can compute it, write it down with respect to this parameter, which is gm over x, over the distance of the small from the big. And this is just, we write down with respect to this L. So putting everything together, we can again write a recursion relation of this contraction, of this sum, that we can put it under control as I showed you. And this resums, boom, to the geodesic equation. So one can say that we didn't do anything, we just rediscovered America, because we just landed on what we should have started from. The point is that even though this is trivial from the GR perspective, because you know that you should start from there, from the EFT point of view, it's highly non-trivial, as I showed you. And the point is that if you want to exploit these techniques to go higher, to higher orders in DSF, you need to have control over this stuff. It's a bit dangerous to assume that the techniques give you what you're expecting. You need to show that they are giving exactly what you're expecting. So, at least in my opinion, it's a crucial stepping stone to go beyond zero SF order. So with this, I will close. So just some concluding points. So seeing the classical GR through the lens of QFT and the techniques and tricks. So the first point that in practice has initiated this whole program is that we can efficiently exploit the knowledge that we already have from particle physics. So people have been doing this stuff for many years, and they know how to compute Feynman integrals, to do diagrammatic organization, to use to regularize their divergences, etc. These are stuff that come also in the classical GR computation. So in practice, why not just copy what we have already done and apply it somewhere else? I mean, this is the smartest thing to do and the most lazy, but it's very efficient here. Secondly, there is an example that I removed due to time, but okay, I can tell you just that there are some, there is a result for the case of the gravitational Bremsstrahlung that using the techniques, the traditional techniques, one cannot land to a closed analytic form. So there is a case that reformulating the problem with these techniques gives you a result that you cannot even compute. So up to now, we have reproducing, let's say, results that have been already computed with GR. But the point is, okay, to justify yourself and your existence, you need to do something novel. And this is a concrete example of a novel computation, the case of Bremsstrahlung. Unfortunately, we didn't have time. So the message here is that we can possibly overcome shortcomings by reformulating in another language the same problem. It's easily applicable to GR modifications. I think this is self-explanatory. And up to now, we have done well in the PN and the PM, but we need to extend also to SF. It's, as I told you, 10 years past. Now, probably we have to start doing it. In the setup that I showed you with the cubic story, the diagrammatics to go into one SF are very clean. It's very specific what you have to do. Of course, the extent of analytic control of this computation is up to debate, and one needs to do it in order to understand exactly at what extent it goes. But from this organization of the computation, at least you can split it into parts and see which part you have analytic control, which, okay, in the end of the day, you will probably need some numerics, which are already used in the SF anyway. The final point is that this is in principle non-perturbative approach. By resumming the flat background the interactions, which is EFT based, can be used for other questions regarding black holes. So one can investigate, and this has been done it has been initiated in other papers for love numbers and their vanishing in D = 4, for possibly long-range quantum contributions that one can have, for higher dimensional black holes, and anyway, whatever one thinks about and can be applied. So, okay, with this I will finish.
Thanks, Stavros. Are there any questions?
Please go to slide number 16.
Of course.
Okay, so you mentioned I guess it's in 4, but essentially the method that applied from EFT and amplitudes describes scattering.
Yes.
We are interested in the bound motion, and you also have this map over there. But to my understanding, this is an incomplete story. This fails.
It is.
At some, I guess, loop order or Minkowskian order. And yes, I was curious what is the status of this, I think, very important piece of map that needs to be understood for these methods to really apply to the observations and gravitational wave observations.
Okay, great question. Thank you. So, okay, here I'm trying to do some rough sketch, so I'm hiding some some secrets of the community, but now they have been exposed. So, for the let's start from the from the first part. So for the PN, these techniques are used, and you can land yourself on the bound problem directly. You know that. I tell it for the rest of the audience to follow it. Now for the PM, that we are doing relativistic approach, we are in practice working in the scattering kinematic regime. This is where we start from, and then we struggle to reshape this information in a way that it's relevant for the bound problem, and this is what these mappings refer to. Indeed, these maps, when you don't have the radiation, because this is the point, the mapping between the hyperbola and the ellipse is a geometric mapping. This B2B maps is a geometric in origin, and the reason why it fails is that when you take the radiation reaction in the problems that enters at some order in perturbation theory, you spoil this geometric map. The status now is that this is still unresolved, as you know, but I think that the most conservative thing that I can say is that one can, again, bring pieces of the computation, for example, the conservative parts, keep these as a mapping, and deal with the rest of the problem of the radiation separately. This is one take. The other is to try to build a complete map of the both conservative radiation reaction terms and try to map it. But this is, I mean, this is work in the doing, and I'm not a specialist, I would say, in this.
But does your self-force approach also?
It has the same problems.
It has the same problem.
Yes, you cannot avoid these problems because the map is the origin of the map is the geometry of the problem that you're just mapping through analytic continuation a hyperbola with an ellipse. It's not something like super crazy.
Yeah, so I have to okay, I'll start with the general one. For the self force, this is when you go from zero self force to one self force. The biggest problem is that when you back react to the metric, then the problem is distribution though, because that's the geodesic is around a specific trajectory, then Einstein equations are nonlinear. They get perfect distribution, and they spend 10, 15 years resolving it.
Mm-hmm.
So does this new methodology give some light on how to resolve this substitution?
Okay, first I have to say that we haven't yet done one SF, so I wouldn't want to sell that we have it and we don't say it. Now in the core, okay, so the reason why these techniques became relevant, there is a secret in the other communities that there was an issue in the handling with the regularizations. So they were using Hadamard, for example, in the PN. What the main thing that these techniques offered is a clean setup to treat the divergences, so DIMREG. Something analogous happens with the SF computations. So, of course, I'm not expecting that we can solve the geodesic equation completely. And, I mean, we have the same equation, the same problems happen there. But the goal is to try to isolate the part that gives you these regularization issues that don't come from the iteration of the geodesic equation. They come from the source. So it comes from the dynamical field and not the motion. And in this sense, if we can isolate that part and understand better how you regulate this, if it can be naturally regulated in DIMREG, then this would already be a big gain, in my opinion. So in a sense, we are splitting the problem in two parts. One is the integrand that you have, and we want to simplify this story. And this actually also is helpful for the PM, because then you can use it as a reorganization of the PM and re-expand, etc. But we want to isolate the part of the integrand. And then again, indeed, when considering the background motion, the iteration of that, then probably we cannot do something better than numerics. So divergence is the point that we are aiming for. No.
I wanted to ask something related to your main goal. You mentioned many times that you want to reproduce the Schwarzschild black hole, and you seem to have succeeded in some sense. But I was wondering, at what point, if you wanted to reproduce the Kerr black hole, what would have been any different? That's one question. And the second is a bit of curiosity. You showed us some recursive relation, which is highly nonlinear. You just, yeah, just that's the solution. How you show that?
So it's not highly nonlinear, first of all. it groups together, it groups terms, so it's several terms in this matrix are diagonal, so it's not that nonlinear as it looks. Maybe the presentation is not very enlightening, but I mean, okay, I can tell the easy one. So with the paper, there is a mathematical file that comes there, and you can press Shift Enter, and you get the solution. There are no UV. Okay, first of all, we don't expect UV. Yes, sorry, I will go to the care. Okay, the care. Okay, the second part is that this is an exact solution. There is no thing, so it is indeed not kind of solution, it is the solution. The second point is that the care is highly more complicated due to two reasons. Here we have a single scale problem, so we have only G. When you include care, you have also the spin, so you have a double expansion. This makes it a more tricky story. So this is the simplest. No, we would not. We would need to also treat perturbatively the spin, which is what happens in PM and PN. Unless one can figure out, I mean, there are works in the spin also that exponentiate and can resum, etc. But in a world like, so there are ideas there. But in the end of the day, it seems that you should expand also a spin, so resum two scales, and the integrands become a bit more complicated, and the extent where you can deal with them, it's obscure to me for now. An easier question would be, for example, Reisner-Nordstrom, that you have two scales, but you don't have the ugly integrands, if this can treat it.
So I think one question.
Just maybe next question. Okay. I don't really understand what is the motivation to calculate something for order to orders of G. Maybe as naive. Okay, conceptually I can see. Practically, to see the expansion of 1 over n plus. The second order is much more logical, just one, and then goes like, I think I'll be happy just to have a couple of let me say, orders of n plus, and that's it. Because is it any phenomenon, or let me say something where one can, I mean, this let me say, all order calculation can be tested for the accuracy of the calculation of the math, let me say, the accuracy of the calculation.
Can I answer? Yes, MRIs. In MRIs, you do these computations. They are relevant. I mean, so there are several studies that show how even the 1SF outperforms very high order of PM expansions. So in the case of MRIs, you are dealing with the exact background space-time, which is all order in G, and you are computing the motion of the small there. And MRIs, not only that you need all order in G to do MRIs, but it seems that MRIs, this SF, perform very well, even in relatively very smaller mass ratios than expected in the beginning, if you symmetrize between the two mass, etc. So the all order in G, it's something that is not irrelevant from a practical point of view, because for LISA and for MRIs, we will have to use this setup. This is actually what is being used. And from the theoretical, it's for fun, as you said.
So I think we should keep the rest of the questions like for the break. So we're a little bit late, so I think we should move. First, thanks Stavros again. And let's move to the next speaker.